Well, good morning, everyone. My name's Roland, and I look after the solution architecture team at Databricks for Australia and New Zealand. And I'm also going to be joined later by Steve Lee from Atlassian. And today we're going to talk about Delta Lake and how Delta solves some of the data engineering challenges organizations face today. Before we jump into Delta, just a quick introduction to Databricks for those that aren't familiar with us. And at Databricks, what we're trying to provide is a unified data analytics platform so that data engineers, data scientists, and data analysts can all come together in one location to help accelerate innovation across their organization. In terms of our company, we've got over 6,000 customers today and many different partners. And although a lot of people associate Apache Spark and Databricks, we certainly expanded our technology capability over the last couple of years. This is such as the introduction of Delta Lake, which brings reliability and performance to the data lake. And this is going to be the focus of our presentation today. We've got ML Flow, which is all around how do I manage the end-to-end ML lifecycle with ease. And then finally, a recent acquisition of Redash, which is for our SQL and BI analysts. So let's have a quick look at what the promise of the data lake was all about. And so the whole goal of the data lake was that we were now able to collect all pieces of information that an organization was looking for, whether this be structured, semi-structured, or unstructured pieces of data. And then we would load all of this into our data lake, and this could have been a Hadoop data lake with technologies such as HDFS, or a cloud data lake with technologies such as S3 or ADLS. And then once we had all this data together, we could then serve it up for downstream analytics and data science. But the challenge was that the data lakes were not really that simple to use, and there was many different reliability and performance challenges associated with them. So let's just go through a few of those. So if we think about from a reliability perspective, when you had production workloads that were running on these file systems, if these jobs failed halfway through, it was really easy to be able to corrupt the data stores. And so what that meant was that there was a heavy amount of engineering effort to go fix those. And also, if downstream consumers tried to query while the data was left in a corrupt state, they would often end up with incorrect results. The Hadoop data lakes often got associated with this notion of schema on read, not schema on write, where we kind of had this philosophy of dumping all the data in and worrying about what it looked like later. But the challenge was this lack of schema enforcement really created inconsistency and low quality data stores for the downstream users of that data. From a performance perspective, we had this terrible small file problem, which meant that if we loaded lots and lots of data onto the platform, or conversely had really big files, we suffered immensely in terms of performance when reading these data sets out. And then finally, to get the scalability and performance that we need, we had to partition our data. And partitioning, also nicknamed the poor man's index, meant that if we didn't know our data structures well that were used for the downstream analysis, or we were trying to structure our partitions around optimizing how we land the data, we often ended up again with subpar performance for those downstream queries. And then finally, as we wanted to expand out the type of capabilities on the platform, the lack of consistency on these data stores made it really hard to mix multiple different workloads. That means reading, writing, and trying to query out all at the same time. And so different patterns like Lambda got introduced and ultimately made our architecture very complicated. And so what this meant was that we had garbage that was landing into the data lake, garbage that was stored in the data lake, and then incorrect or garbage analysis that came out of it. So what is Delta Lake all about? And so, as I said earlier, Delta is designed to bring reliability and performance to the existing data lakes, whether that be technologies such as HDFS, S3, or ADLS. Now, Delta in itself is an open format system based on Parquet, but what we're trying to bring is an additional capabilities such as transactional support, and also make the transition from the existing Spark APIs to Delta as seamless as possible to make sure that we can easily migrate workloads from existing technologies such as Parquet to Delta. At the end of the day, what this enables you to do is now bring in batch workloads, streaming workloads, and also capabilities that engineers love, such as updates and deletes, to existing file stores that didn't necessarily support these capabilities. Now, when we brought those all in Delta, this ultimately means that we can now pump out high quality and reliable data for our downstream analytics. So to highlight how Delta solves these various different challenges on the data lake, let's look at a particular use case and run through it. And so the goal here is what we're trying to do is look at particular airport and airline information and rank airplanes according to their flight delay schedules. And so this will need to combine 3 different data sets: a near real-time data set around flight information with a flight event history. We have a plane data set, which contains all current and historical information around an aircraft, which will be stored in a slowly changing dimension. And then a weather data set, which will contain public weather forecasts, which will be updated around every 5 minutes. And so the goal will be that we bring all these data sets in, we curate the data into a silver data store, and then we aggregate up this data for our ranking into a gold layer for querying and analysis. So let's have a look at what this looked like before we had Delta. And so we'd have our 3 different data sources, all of a varying different frequency of data being loaded in there, and different ways that we'd ingest those into the platform. And so for our near real-time feeds of data, we're probably using something like Kafka, and then a stream that's going to read that data in real time and then sync that data into Parquet into my flight silver table. For my plane information, which was a slowly changing dimension and stored in CSV format, I'm probably only going to schedule that on a batch basis as needed. And then finally, for my weather forecast that also gets ingested around every 5 minutes, we're going to use a JSON reader and schedule that on a basis, also storing both of these in Parquet files in our silver layer. We would then to create our gold layer on a scheduled batch basis, aggregate all of these 3 tables from the silver layer and create a new gold layer that has the delays per airplane also stored in Parquet. Now, do we anticipate any problems as we're going through this process? Well, let's look at some common different challenges and problems that might face along the way and how we help solve those. So the first one is, well, what happens if one of these production jobs fails halfway through? So let's look at the weather information. Let's just say we're loading this every 5 minutes, and on one of the runs, this data fails to complete, and halfway through, some portions of the data are left in this silver weather table. And so what this means is that this table is now left in a corrupt state. There's partial data that's been loaded into the table. And then for our gold level aggregates, that also then gets corrupted, because the next time that the job schedules to aggregate the data from these 3 silver tables, this table will now also be corrupted. Now with Delta, we help solve this challenge by using ACID transactions. And that means either data loads and transactions either succeed or fail. And it means it's not possible for half data assets to be loaded into particular tables. The second challenge is around the lack of schema enforcement. So let's say we deployed a new job into production and accidentally introduced some incompatible schema changes. So in this example here, we're getting some new flight information. And as you know, there was already many different schemas that we might have available. But if one of these doesn't match this schema, what that would mean is that when we try to create this aggregate gold level table, this would also fail. And so what we're trying to do with Delta is avoid this happening. And so with Delta Lake, with schema enforcement, we can make sure that as the data is being loaded into the silver table, that only data that matches the particular schema and format is loaded in there, alleviating this whole issue of corrupt data and subsequent data failures for our downstream tables. The third challenge is lack of consistency. So what happens if we had multiple different jobs all running at the same time? So in this example here, we've got many different feeds of data and also some aggregate tables that are being created from these downstream feeds. And so each of these is on a different schedule. So it's likely that these are going to be concurrently scheduled at the same time. And so let's have a look at the example of, let's just say we're partially loading this weather data set that comes in every 5 minutes. But we also have another scheduled job that creates this gold level aggregate. If halfway through this write that's being progressed, we try to create this gold table, only partial sets of information that in this silver weather table would be available for this gold table analysis. And so again, we would corrupt this table by partially data sets being made available. Again, back with Delta, if we use these capabilities such as ACID transactions and also the ability to now do batch and streaming all on the same table, we alleviate these problems that are associated with consistency. The fourth challenge is, well, what happens if we have a data loss or a data problem? So in this example here, let's just say a new job is deployed into production that actually specifies the mode as overwrite, which means that we're not going to append this data set. We're now going to erase and reload it. And yes, this can happen because, again, people are writing code. And so this job would get deployed, and what would mean is that this flight data set is now disappeared. And so all of our historic data is gone and not available anymore. Now with Delta, we have the ability and a capability called time travel. So even if the user accidentally did do this overwrite mode, we keep a version of these tables inside Delta, which means that we can roll back to a previous version easily and restore the data that was accidentally deleted as part of this process. The fifth challenge is around the small file problem. So what happens when a lot of small files or small Parquet files start getting added to this silver layer? And so this is particularly prevalent in streaming workloads. So as we know, this was a near real-time stream of data that was coming in from my flight information. So imagine this is a stream that's continuously ingesting data, and every time it ingests data, it creates a new Parquet file. Now, the challenge is that we also have other small data sets coming in from our other feeds. And then when we try to then query these and aggregate those again for our gold level aggregates, it's really, really slow to be able to do this. So with Delta, we have a feature called compaction, which we can either auto compact when we load the data in, or we can batch compact that, depending if we want to balance our performance or latency. And then we also introduce a capability around data skipping, where in the Delta logs, we keep track of all the data that's being loaded in there, and we index the columns so that we know which information is relevant to what files. So that means that when we are doing those downstream querying on top of these tables, we can skip over data that's irrelevant to the queries that we're trying to access. The sixth problem is that, partitioning is static. So as we talked about earlier, often partitioning is either designed around the known query patterns when we create these workloads, or for ease of data ingestion. But what happens if those data access pattern changes, or when we load it for ease of ingestion doesn't match how our end users are wanting to query that out? Well, with Delta, again, we have indexing capability and data skipping. So what that means is that, again, we keep track of all this information separately to the Parquet files in the Delta log, so that as we write more selective queries or queries that only access subsets of the data, we don't have to scan all the pieces of information out of every single file. We know where that data is located, and we can more effectively and easily query that data out independently of whether that data was partitioned correctly or not. And then our final problem is around GDPR compliance. So what happens if we want to change an individual record? Now, again, these file stores are generally immutable by default, meaning we can easily append to them, but it's really hard to modify an existing file that's been loaded. Now, the great thing is with Delta is that we bring update, delete, and merge capability, meaning these type of workloads that were traditionally not possible are now able to be done with Delta Lake. So if we summarize those all up, how does Delta make this a reality for you to be able to use these particular capabilities? So in terms of, data appends, modifications, job stability, real-time blending of data sets, and keeping historical versions of data, Azure Transactions really neatly covers all of these. And with this broad set of capabilities, have all of these data engineering problems covered off. One of the other big challenges is around the scalability and performance. And again, we use Spark under the hood to give us that distributed and scalable nature to manage the large amounts of metadata and files that we store in these Delta lakes. And the issues around the too many smile problem, things like auto indexing, really helps us get around the issue of reading what's relevant for the queries rather than every set of information that we have. And then finally, to resolve the data quality issues, the schema enforcement and evolution makes it really simple and easy to make sure that we have high quality and reliable data in Delta Lake. So with that, I'm going to hand over to Steve Lee from Atlassian, who's going to run through a use case of how they use Delta to help GDPR.
Hi, my name is Steve Lee. I'm a principal data engineer at Atlassian. Today, I'll be talking about how Atlassian are using Delta in our data lake, Socrates. First, a quick introduction to Socrates. Then I'll explain the problems we have been having with our traditional solution. Then I'll show you how we are using Delta to solve these problems. And finally, I'll wrap up with our future plans for Delta. Socrates is Atlassian's data lake. We have all kinds of data in our lake, including behavioral events, business intelligence, including financial and customer data, marketing data, and internal analytics data, including HR and incident and SLO tracking. Socrates is serving over 2,000 monthly active users. Socrates is built on a few core technologies. Amazon S3 is used for all data storage. Databricks is used for compute, including interactive notebooking, as well as ETL and job processing. And Redash is used for data visualization and dashboarding. How does Socrates handle personally identifiable information, PII? Well, we avoid storing PII whenever possible. We have a single lookup table of UUIDs to PII data. Our users can request temporary access to this table to perform joins with other datasets. The table is rebuilt daily from the source system in the identity team. This ensures users who have requested to be forgotten under their rights provided by GDPR are removed from the table. This solution seems to work acceptably. But what are some of the problems we need to consider? There are 3 scenarios. First, the right to be forgotten. This is mostly handled by the lookup table. However, this solution doesn't scale well. The second scenario is accidental data capture. Unfortunately, accidents do happen, and we need a process for cleaning up data that has been captured inappropriately. And finally, when a customer is deactivated, we need to ensure that any data they own is removed from the lake within 30 days. Socrates also avoids storing user-generated content for this reason. In the places where we do, we currently only keep the last 30 days worth of data to comply with this. The common theme here is that we need a way to selectively delete or update rows. So how would we do this in a traditional ETL world? First, we would copy the data to a new location while applying the necessary filtering. We verify that the filter has correctly removed the data we wanted. Then we create a backup of the existing data and then delete the existing data. At this point, our dataset is now offline. Now, we copy the corrected data back into the original location and verify data integrity. Finally, we can clean up the copies. Overall, the dataset was copied 3 times. This is slow, expensive, and error-prone. If the original dataset was being updated in streaming, we also have to stop ingestion for the whole duration of this process. Even if it was being updated in batch mode, we have to take the dataset offline during this process. There has to be a better way. And indeed there is. Delta Lake solves these problems. Delta Lake allows us to use natural delete and update statements. There is no complex data copying, no need to shut down the ingestion pipeline, no need to take the dataset offline. What does this process look like using Delta Lake? First, we perform a delete or update statement on the dataset. Internally, Delta Lake generates a new version of the data. When the data is ready, it goes live. Delta allows us to perform these updates and deletes in place. There are no multiple copies. Atomically, the dataset doesn't need to go offline and no one sees a partially updated dataset. And reversible. The backup is implicit in the version history of the table. Finally, we can use a vacuum statement to ask Delta to discard previous versions. The cutoff is configurable. For removing customer data, we would choose versions older than, say, 25 days to ensure we meet the 30-day deadline. To clean up an accidental data capture, we would remove all previous versions to ensure the bad data is permanently deleted. What about legacy tools? We still have a lot of users querying through Amazon Athena. The first option is an in-place conversion. After vacuuming all previous versions, you can delete the Delta log and the table reverts to being a plain Parquet table. If you prefer to keep the table in Delta format, you can use a manifest table. This is when Delta creates a manifest listing all the files that represent the current version of the table. Hive-based tools can use this list to read a Delta table. Finally, our future plans for Delta. Firstly, we would like to automate the GDPR cleanup tasks. Rather than rebuild the UUID table from source daily, we plan to subscribe to write to be forgotten requests on our internal message bus and automatically issue delete statements. This approach should scale much better and allow us the flexibility to include PII data in other places. Finally, we want to use Delta Lake as the default format for all new datasets in Socrates. To achieve this, we first need to migrate the remaining Athena users over to Databricks, and we are currently rebuilding our streaming ingestion framework to land data using Delta format. We believe that Delta Lake is vital for the future success of Socrates.
Thank you, Steve. Well, I hope you really enjoyed the session that myself and Steve have run today. If you're keen to learn more about Databricks, we're hosting a virtual event on the 26th of August, a Unified Analytics Bootcamp, where you'll get an introduction to a little bit more around Databricks. Plus, we're also going to run some hands-on labs with Delta Lake and MLflow. So you'll get an opportunity to actually use the product and see some of the technology that we discussed in the session today. It's going to be running from 9:30 a.m. to 1 p.m. and you can use the QR code or the link on the screen to register. Hope to see you there.